Please, thank you.
All right, so hello everybody. Hi Miguel. Thank you very much for having me in this very nice Swampland seminar series. It's my pleasure to speak. And of course, please interrupt me anytime. This should be an interactive seminar, so if there are questions or comments, please react immediately. In fact, I like to talk about the Swampland at a large number of space-time dimensions. That's the title of my talk. And let's see, now I got stuck somewhere. Yeah. The work is joint work with Quentin Bonnefoy, Luca Ciambelli, and Severin Lüst, and it appeared last year in a November preprint. So I think in this audience, I don't have to give a very elaborate introduction into the Swampland program. One can rephrase it, I think, putting the question, which infrared consistent quantum field theories cannot be embedded into a UV complete quantum gravity theory. So this question arises in several rephrasement, and that is called the Swampland program. I can also show you this nice picture by Aaron. We have the UV quantum gravity or string theory, and if you go down in dimensions, also if you go down in energy, we get the landscape of consistent effective field theories. But from the effective field theory point of view, there are many more consistent EFTs, and many of them cannot be obtained from a UV complete quantum gravity theory. And this part of this picture is then called the Swampland. Very often when we discuss the Swampland, as I have mentioned already, there's an effective field theory, and the effective field theory typically breaks down above a certain scale, and we call this the Swampland scale lambda, which can be viewed as a cutoff scale. And indeed, if this Swampland scale lambda is lower than any characteristic energy scale, then the entire EFT would even belong to the Swampland. Very often, as you know, there's an infinite tower of states above the scale lambda, and I will show you this picture a few times more. So you see the Planck scale here, the Planck scale in the effective theory. Here we have the cutoff lambda, or the Swampland scale lambda, and above this scale lambda, a tower of states is opening up. So lambda also typically is given by some coupling constant times the Planck mass. And we have very known examples. For example, this tower can be comprised out of KK modes. Then lambda is of order 1 over R, where R is the typical KK scale, say the scale of the internal compact dimensions, and the associated coupling constant is also proportional to 1 over R. We can also have the case where the tower is built by the string modes. In this scale, lambda is typically the string scale, and the associated coupling constant is the string coupling constant GS. So this is the general framework, and today the question I like to ask is large D is the number of dimensions of space-time dimensions, is large D quantum gravity part of the Swampland or part of the landscape? The affirmative answer is known, in particular in string theory. There we know that we have a critical, so-called critical dimension, 10 or 26 for the bosonic string. So indeed, if we take this answer, if we take this critical dimension, we know that large D quantum gravity would be in the Swampland. But here we suggest a complementary approach, namely we want to consider the number of dimensions as a new Swampland parameter. And in particular, we want to look at circumstances where this cutoff or the Swampland scale lambda is a non-trivial function on the number of dimensions. So lambda is a function of D.
One question I have, Dieter, is the notion of what do we mean by the dimension here. You're not
necessarily talking about the Minkowski background, right?
I will come to it. I will basically consider frameworks where both the uncompactified and also the compactified number of dimensions is taken as swampland parameters. So I will particularly also look at circumstances where the dimension of the effective feed theory, say, and the number of dimensions of the internal part of the theory is coupled to each other. But this is a priori not determined. Okay, so also to give proper reference, there's a very nice set of previous papers, mostly in classical gravity, where people have looked at large D gravity theories, and this was basically pioneered by the work by Roberto Emperor and others. So if you wish, our work is a kind of quantum gravity, quantum or swampland generalization of this work. So here is a quick outline of my talk. I first want to discuss with you a kind of slightly changed version of the large distance conjecture, namely we call it the negative distance conjecture, NDC. And we will use this then to formulate the so-called large dimension conjecture, LDC. And after this, I will apply the LDC in particular for ADS backgrounds. And finally, I also want to give an outlook, and I want to briefly mention one particular, maybe a new kind of duality symmetry, which we call d-duality. All right, so let me start by mentioning a few swampland distance conjectures at large D, and then I will come to the NDC, the negative distance conjecture, and the large dimension conjecture. Namely, first, let's have a quick look at the big gravity conjecture at arbitrary D. And throughout my talk, a little d is basically always the dimension of the effective theory, and capital D or capital D will denote the total number of space-time dimensions. So I start with the simplest version of the weak gravity conjecture, namely in 4 dimensions. We know that if we have a U1 gauge theory that is coupled to quantum gravity, there must be a so-called weak gravity conjecture particle, MQ, particle whose mass MQ must be smaller in proper units than its charge times coupling constant GU1, and all this is measured in proper Planck units. So this is the weak gravity conjecture in 4 dimensions, and one can generalize this now to arbitrary dimensions D. That is, I think, was done in a nice paper by Heidenreich, Ries, and Rudelius. So the generalization considers a p-form gauge field that is coupled to a p-1 brane. And then as a generalization of this formula, one gets this bound where T is the tension of the p-1 brane, Q is a charge which also has some certain dimension, G again is a coupling constant, and here is a prefactor which depends on the degree of the form on P, and also on D on the number of dimensions of the effective theory. So you see that this is already a bound which depends on the number of space-time dimensions. And in fact, the strongest bound is obtained when setting P equals D over 2. So if the dimension of the brane is approximately half of the space-time dimensions, so then you can simplify the formula, and what you get is that square root of D times the tension must obey this particular bound. So you already see that there's a bound on the number of space-time dimensions which is arising here, given in terms of the inverse tension of the brane. And we will basically encounter this kind of bound also in our future discussion. All right. So now let me come to the swampland conjecture, which I will use now most in my talk, namely the swampland distance conjecture. And this states that at large distance directions, and I will call the distance capital delta, namely at large distance directions in the moduli space of string vacuum or of quantum gravity vacuum, there must be an infinite tower of states associated to some mass scale little m. And the swampland distance conjecture now is stating that the mass scale m is associated to the Planck scale times the exponential of minus this distance delta, which means that the EFT breaks down for large distances, namely where delta goes to infinity. In this case, m becomes very small, and this is precisely the situation where a tower of light states of light masses is opening up. We can make this a little bit, we can generalize this slightly, namely that in general data determines the geodesic distance in a certain phi parameter space of backgrounds in gravity. So in general data is a function of these background parameters phi. And one can nicely obtain this functional dependence in the following form. Usually one has certain massless fields associated to the background parameters, and then there is an effective action associated to these fields, which has typically this form. There's a kinetic term, and possibly there's also a potential term. Here capital phi denotes the canonically normalized field, which is a function of the field little phi. And if we formulate things in such a way, the distance delta can be immediately read off. It is proportional to capital phi times some so-called exponential fall of parameter lambda. And this form will be also important for our future discussion. So I have already mentioned compactifications. And for string compactifications, the swampland distance conjecture is often due to the higher dimensional nature of the theory. Then the tower mass scale is nothing else than the Kaluza-Klein mass scale, which is proportional to 1 over r. And the associated distance goes like the log of r. And for large radii, you see clearly that the distance becomes very large. Of course, having this formula, you might also know what happens in the opposite limit where r goes to 0. In this limit, the KK modes typically are heavy, and the geometric picture gets lost because the KK modes, one can say, build up the compact internal geometry. But very often, like in string theory, there's a dual tower of winding modes that get light in this limit. So there's a second tower, a dual tower, whose masses are not proportional to 1 over r, but they are proportional to r. And there's another distance. In this case, it goes like a minus log r, and the winding distance therefore gets large for small values of r. So this is a well-known situation, I think, which is rather clear and obvious. But one can also, I think, state, namely, if there is a situation where it happens that there's an infinite distance limit without a corresponding light tower of states that satisfies the SDC, then it cannot be possible to approach this infinite distance point. Then this infinite distance point should be obstructed. And in fact, this is precisely, I think, the observation we like to use now in the following, namely, in the following, we like to basically reverse the logic and define, let's say we have identified a particular tower in our effective field theory. And for a particular tower, we now like to define, and this particular tower is, say, given by some states little I, and therefore for some particular tower, we now like to define a quantity delta I as minus the logarithm of the mass scale mi for this particular tower. As before, there might be also a possible dual tower of states denoted by I tilde, and there therefore might be also a dual distance delta tilde, which is again given by the minus log of the tilted masses. So this is basically how I like to define now delta or delta tilde respectively. And with that, now we like to formulate the negative distance conjecture NDC, namely that for a particular tower, little I, an infinite distance limit, delta goes to minus infinity, is obstructed, which means not allowed, unless there is a dual tower, I tilde, which becomes light in this limit. So this might be a little bit unusual definition of the distance, because it also can become negative. Geometric distances should not be negative, but in the way I have defined delta, it also become negative. And in this way, we also now can define this negative distance conjecture. We should not have towers of states whose distance functionally becomes negative unless there is a dual tower of states I tilde.
So just want to make sure, how does this fit with the M theory and going on a circle? Just want to compare that.
I could, in fact, discuss also the M theory. I have it on my last slide. In M theory, the situation is a little bit more tricky. I mean, for M theory, we know that we have Kaluza-Klein modes, but a priori there, it's not so clear what is a dual tower of states. And we know, for example, that we could put M theory not on a circle, but on a two torus, say, and then the RAP membranes would serve as a dual tower of this. This is something which I'm thinking about at the moment, but I think M theory also is not a counterexample, if you wish, to this negative distance conjecture.
Why is it not? I didn't get it. Why is it not a counterexample? Why is M theory on a circle not a counterexample?
But at the weak coupling limit, we get all the tower of string excitation modes that become light, right? So there is a tower in both limits.
If you wish M theory on a circle, for M theory on a circle,
you mean that it's not dual, right? So the question is what dual means.
The limit is obstructed, because then you would go to the limit of strong string coupling, right? And I will explain this on my last slide. So of course, in this sense, the negative distance conjecture is a strong assumption. I will tell you on what kind of assumptions the NDC is based. But I think M theory still fits nicely into this.
Yeah, I think as Irene is saying, it would fit nicely if you by duality you don't mean the usual sense. That is, you can have a KK mode on one limit and the strings in the other limit. That's fine.
That's right.
That's a sense in which you want to have. In other words, you cannot have only a weak coupling point, and the other side there should be another weak coupling point.
That's right. That's right.
Yeah, so that's the sense of negative distance conjecture for you.
Yeah.
Yes.
But it's true that even in M theory, the dual tower, the KK mode are D0 branes, so the dual towers are D6 branes, and D6 branes indeed do become tensionless relative to the Planck scale at weak coupling.
Yes.
And so it's exactly.
Yeah, I was going.
Yeah, there's always.
I want to say the same now, but it's not the leading tower, but it's true that also the dual tower becomes.
That's the relevant dual tower. There's always a dual tower.
But M theory is indeed an interesting situation, and I'm trying to make this also clear. But in any case, the NDC I think would fully apply if there's really a situation where there is no dual tower of state, and I think then this limit should be obstructed and not be possible. So I can show you this again in a few pictures. So this is the standard scenario where there's a tower which is lighter than the Planck mass, and this is then associated to a positive distance delta I. This is what we think about usually. And indeed, in terms of Kaluza-Klein modes, it means that the KK masses are smaller than in Planck. The associated couplings are also weak. I mean, the associated GKK, or in terms of string theory, GS, is smaller than 1. And it also means that the effective Planck scale in the effective theory is always bigger than the fundamental Planck scale, say, in the capital D-dimensional theory, or is always bigger than the string scale. So this is the standard situation, I think. And now for the NDC, we would have this situation that the distance delta I is negative. The tower is starting above the Planck scale, and the NDC says, no, this situation is not possible. It is obstructed. And why it could be obstructed? Because the KK masses, I mean, this is obvious, are bigger than Planck, so there is no good geometric interpretation anymore. We have large couplings, so at least the effective theory is not anymore controllable. And with that also the effective Planck mass becomes smaller than the fundamental Planck mass or the string scale. But unless there's a dual tower where always, where now things are opposite, M tilde is smaller than M Planck, G tilde is smaller than 1, and the Planck scale is again, the effective Planck scale is again bigger than the fundamental Planck scale. So in other words, if there's a dual tower of states whose cutoff scale, whose Swampland scale is below the Planck scale. So applying the NDC, we are then particularly interested in possible situations where there is no dual tower, because in this case, I think one can get also some interesting constraint from the NDC. Of course, also the situation with a dual tower of states might be also interesting. Good, I have already said that these tower masses typically depend on some geometric parameters. But as we know already, they may also depend non-trivially on the number of space-time dimensions. So in general, M is not only a function of the geometric parameters phi, but it is also a function of the number of dimensions. And this now brings us to propose to include D also as a Swampland parameter. So we want to take D now really very seriously as a Swampland parameter. And in view of what I have said before, this is a little bit unusual because there is no dynamical theory of D, and there is no kinetic term for D in an effective field theory description, at least not really in a known way.
So Dieter, I'm a bit confused here. So when you say M is a function of phi and D, phi can get a meaning in different Ds, has different meanings. For example, phi could be the radius of a circle in dimension higher or lower. And so it's not like phi is always there for any D. So what do you mean by M of phi and D?
Okay, well, in a moment I will take phi again as a radius of a compactification, so as a typical scale of some compact space. And D is the number of space-time dimensions or space dimensions of this compact space.
So in that context, I understand. In that context, I understand. But I'm just saying, in general, I don't understand it. In other words, for specific cases, it may make sense, but not as a general statement. Are you going to only apply it for specific cases?
Yes.
Okay.
In the following, in fact, I will basically apply to specific cases, namely where we know how some particular tower depends on phi and depends also on D. So these are indeed it's a restricted set of data or a restricted set of cases. But what we also would then at the end of the day think would be nice to formulate a distance conjecture which really determines the distance between space-times of different dimensions. So setting up a kind of functional which also depends on D and which cannot be really a standard geodesic distance within some given set of backgrounds, but it would be also the generalization that delta of D determines the distance between space-times of different dimensions. So this would be the final aim. And then it would not anymore really rely on particular specific cases. Okay, so
maybe, sorry, before you continue, can I ask one more thing?
Yes.
It's just about the definition of delta.
Yes.
It's related also to the first question. So should I define a delta for each tower of states that is becoming light in the limit, or should I consider only the leading tower?
In particular, I would like to have for each tower one particular delta, and depending on your ambition, you could say that the NDC should apply for each tower, so to say, in the theory. Then it would be, of course, a rather strong statement, or it should only apply, say, for the leading tower.
Mm-hmm.
But let's say for each tower we find in our theory, we like to define a particular functional delta.
I think this negative distance conjecture, in some sense, is it not equivalent to the statement that any infinite distance is a weak gauge coupling limit? Because then there's always the electromagnetic duals of the towers that become states.
I think in the known cases that's what it is, and I had it on my previous slide.
If this is a weak coupling limit, you just do electromagnetic duality and you get the dual tower, I think.
But certainly we do not know whether for each tower there is a dual magnetic tower, so to say. I mean, this assumes that there's a dual magnetic tower, and I think I can show you later on particular example where there is no dual tower. Where in other words, where there is no electric magnetic duality.
I think that's a nice comment. The problem is that it could be that sometimes by doing this electromagnetic duality, the dual tower is a tower of instantons or something like that, and no longer of particles.
I think that it's equivalent to the statement. I mean, there is some sense a conjecture that goes around. I don't know if it's proven or not, that every infinite distance limit is a weak coupling limit of some gauge field or gauge coupling. I think if that's true, then there's always a non-abelian. There's always a dual electromagnetic dual.
Yeah,
tower.
I mean,
the other way around.
I think
if at the end of the day we find for each weak coupling limit also a dual magnetic limit, which is then weakly coupled on the opposite side, then it's fine with me. But I would not a priori believe that this can be always done.
I mean, I actually propose that it can be done, but having in mind like P4 gauge fields, which also includes axions. And that's why I say, like, if you dualize it, could be that the tower, I mean, in one of the frames, right, the dual is the tower is going to be instantons, so it's not really like a tower of particles.
Okay, this is something we can certainly debate about, but
let's discuss later, yeah.
We can debate about, but say if I state my assumptions, then I think I can also work within this given framework.
Yeah, please go on.
Good. So let's now accept that we have this that we have D as a new Swampland parameter, and with that now I just basically rephrase again the NDC, and I call it now the large dimension conjecture LDC. Namely, I formulate in such a way: if there's a tower of states I, the corresponding distance function of the EFT fields phi and of the dimension D must be positive. So delta I of phi of D must be a positive function, unless there's a dual tower of states I tilde such that delta tilde becomes positive when our original distance changes its sign. So basically, if there's a zero, there are two possibilities. Either we have to stop basically at the zeros of delta unless we have a dual tower of states. And basically what we want to do is we want to be now careful in examining these functions, not only as a function of phi, it is, I think, done usually, but now also as a function of D. And as we will see, the LDC will typically put bounds on D as a function of the other background parameters phi. And this is also natural to expect that we will not get a priori an absolute bound on D, because we have a multi-parameter space where D is just one of the parameters, and therefore we will get bounds where some critical value of D, call it D0, will depend also on the other background values of phi. Okay, and this is precisely what we will also find in the following. Good, so this is a general framework. We had some discussion about it. Are there still further questions? But then I will basically come now to some specific cases. Okay, my specific cases will be again compactifications, and to prepare for that, I again show you some formulas which I think are well known, but let me just very quickly recall them. So I have a volume modulus phi for some compactification for some compact space of dimension d prime, and the following d will be always a dimension of my effective field theory. D prime will be the number of dimensions of my compact space, and capital D, which is somewhere written also, is simply the sum of d and d prime. So the volume of d prime is given basically by the exponential of d prime times phi. Here we have the well-known relation between the effective Planck mass and the Planck mass in the higher dimensional theory. We can use these relations to derive the effective action for little phi, which contains as a prefactor the effective Planck mass, the Ricci term, and the kinetic energy term for phi with this particular dimension dependent prefactor. I told you before that I should also figure out what is my canonical field, capital phi. It is given in terms of little phi or in terms of the log of the volume in this particular way. And then I can put things together, get the mass formula for the kk masses that scale with the volume in this way, or in terms of the canonical field, we get this precise relation between the kk masses and the canonical field. And this, of course, exhibits the tower behavior, which I have shown you before. But this formula is nice because we have, so to say, singled out phi and also the dimensionful, I mean, the prefactor lambda that depends on the number of dimensions. So if I put this together, delta is lambda times capital phi. Lambda has this form. And again, I see a behavior which I shown you before. If I, for example, put d equals roughly equal to d prime, I get that lambda scales like 1 over d, square root of 1 over d, which goes to 0 for a large number of dimensions. So the fall-off parameter lambda goes to 0. But this is not the end of the story, because in general, also the value of the canonical field will also depend on the number of dimensions. And basically what I get, it might sound rather trivial, perhaps it is also simple. The LDC bound basically tells you that the field value of capital phi must be positive as a function of d and d prime, unless there's a dual tower of states. Okay, so this is what I like to examine in the following. And I want to do it basically following up the idea of the large distance conjecture for ADS, for anti-de Sitter backgrounds. So let me also very briefly recall this particular conjecture. Namely, we want to consider ADS d vacua in quantum gravity with varying negative cosmological constant lambda. And then, and this is work with Eran and Kumrun from roughly 2 years ago, one can formulate the ADS distance conjecture, ADC abbreviated, which tells that there should exist an infinite tower of states with mass scale m that behaves like, basically like lambda, the modulus of the cosmological constant, raised to some power alpha, where this parameter alpha should be always bigger or equal than 1/2. That is the ADC. And it also has I think, the interesting consequence that the anti-de Sitter spaces of a certain dimension, little d, cannot exist alone as a consistent background. This because the flat limit of ADSD should be always accompanied by an additional tower of states. So basically, another part of space-time dimension should open up in this limit. And this certainly also has some interesting implications for the dual CFT descriptions, which was also discussed, I think, in these two interesting papers. Okay, The strong version of the ADC tells even that alpha has to be equal to 1/2, and it is in fact saturated for supersymmetric ADS structure. So again, we have the same kind of picture as we had before. There's an infinite tower of states above lambda. And as we know, this conjecture is satisfied for many known backgrounds of string and of M theory, like, for example, ADS5 times S5. Here, indeed, via a tower of KK modes. But I think in general, it's also not a priori clear whether the tower always is given by KK modes. It can be also string modes or possibly other modes which are responsible for the ADC. So what we want to do now, we want to generalize basically ADS5 times S5. We want to generalize it to arbitrary dimensions. So instead of ADS5 times S5, we consider backgrounds of the form ADSD times SD prime, with D plus D prime equal to capital D. And therefore, a priori, we have two scales, two radii, one for ADSD, which we call RA, and another radius for the compact part of space for SD prime, which we call RS. There are two corresponding Ricci scalars, RA, which has this particular form, and RS, which takes this form, again with some dimension, number of dimension dependent prefactors. In order to get solutions of the equation of motion, we also introduce a D-form gauge field of this form. So there's a D-form gauge field of this particular form, also as a generalization of what we know from ADS5 times S5. I think this kind of compactifications are called Freund-Rubin compactifications, so it falls precisely into this class of backgrounds. Solving the equation of motions gives a relation between the two Ricci tensors RA and RS of this form, where F is the number of, if you wish, you can call it the flux number, which determines the background field capital F. And from that, we see that there's a precise relation between the external radius, the internal radius RS and the ADS radius RA of this particular form. So they cannot be chosen to be independent from each other, and the relation between RS and RA depends on the number of dimensions in precisely this way. Okay, so this is, I think, rather simple setup. One can continue and now compute the KK spectrum in the effective little d-dimensional theory. One can do it by using the internal Laplacian on SD prime, and one gets the following formula that the KK masses go inversely with RS square, and the numerator contains the number of d prime in this particular way. So this is also a simple formula which we will now use in the following. And to simplify things now in our paper, in fact, we discuss various cases, but I think the simplest and most interesting case is the following, where we say that the sphere radius and the ADS radius are of the same order. So we just we eliminate one and we introduce one common scale called capital R, which also implies then from the formula I have shown you before that the dimensions of the ADS part and the sphere part must be the same. So it implies that D equals D prime equals capital D over 2. And then I can put these back into my previous formula for the KK mass. I also want to consider the proper rescaling of the effective Planck mass in terms of my effective Planck mass, and the rescaling factor in this case is just given by R over square root of D. This one can also figure out quite easily. So putting all this together, one gets the following simple formula for the KK masses, namely that MKK square in units of the little d-dimensional Planck mass is just given by d over r square. So the kk masses depend on the number of dimensions, capital D, and on the radius of ADS or S. It is the same in this particular way. And indeed, what we find here is, of course, the well-known scaling behavior of the ray in terms of the radius, but we also find an interesting, I think, dependence, a simple, interesting dependence on the number of space-time dimensions. So I like to emphasize again that we did not put any further restrictions. We can really treat capital D as an arbitrary parameter. We are also not restricted to the critical dimension of string theory. And we just want to see whether from this rather generic and simple consideration, one now gets a bound on the number of space-time dimensions. So from what I said before, it is now again easy to continue. We determine our canonical field phi. It is just a simple rewriting. We get the ADS distance, which is given by this expression. And now we get, as a large dimension conjecture, we get the following LDC bound, namely that D must be smaller than some particular value D0, which in this unit is just given by R square, the square of the typical scale of the theory in question. So what is happening is also clear. If D gets bigger than this limit, the kk masses become super Planckian above D0, and the notion of space-time geometry is lost. And therefore, we request, if you wish, that D must respect this bound, because the NDC or the LDC is telling us that this limit would be obstructed. So this is the way how we get the bound on the number of space-time dimensions. And of course, we could think about also several different towers, and we could do this. I have chosen basically the most simple one. I think this formula also has an interesting and neat geometric interpretation. Namely, if we look at the mathematical formula for the volume of the unit D-sphere, it is given in terms of the inverse Euler gamma function. And if you expand this for large D, you get precisely the same behavior for the volume, which we got in a way from different reasoning. Namely that the volume of SD goes like R over square root of D raised to the D's power. So indeed, for large D, we see that the kk masses precisely follow this mathematical formula for the volume of the D-dimensional sphere. And basically what we are saying, the LDC puts a bound on the volume of the D-dimensional sphere in Planck units, that the volume should not become smaller than 1. Okay.
Dieter, sorry, can
yes.
I ask you a quick question? Maybe you explained this and I missed it. So if that's the case, I'm sorry. But so when you're defining M Planck, there's usually a factors of pi that whose power depends on the number of dimensions, right? So yes. Does that play a role here? Is this something we should be careful about? Like, you know, there's different definitions of M Planck, like the thing in front yes. of the Lagrangian or.
Okay, yeah, right. very well. I think we were a little more careful with the powers of pi, and you see also powers of pi here in this formula. They could give some additional factors also here, but the main thing is that D is restricted by the scale of the theory. But if you are careful and work it out, I think there might be some additional powers of pi that sneak into this bound. That is correct.
Okay, thanks.
But I think the main conclusion or the qualitative feature of this bound will not be changed by these additional powers of pi. But essentially, I will come to this problem in a second, because you might also want to ask, I think it comes on one of my next slides, you want to ask, I mean, this is a bound on D, which is not an absolute bound, but it depends on R. But you could ask could we also obtain an absolute bound on D? Say something like even which looks like the critical dimension of string theory. And if one does this, then of course one has to be careful with the powers of pi and so on. And I will mention this in a second. Okay, so what could be the microscopic reason? I mean, for the bound. I mean, we have now two options. We take it as it is, or we look for a dual tower. If there would be a dual tower, then of course we could also enter the regime where D becomes large, because if there's a dual tower which opens up at large dimensions, then basically we could cover the full range of all possible dimensions. But I think we have a good argument why the LDC is really very strong here, and this is because of flux quantization. That is also something which we still have to work out with all the factors. But basically, it tells you if I told you the LDC is basically telling you that the volume of the sphere should be always bigger than 1. And this is, I think, basically implied also by the requirement of flux quantization. So for ADS times S background, I think that the microscopic reason why we have a bound on the dimensions in terms of R is precisely given by flux quantization. So it seems, at least to me here, that due to the topology of the sphere and due to flux quantization, there is no dual winding tower here, which we can take. I mean, this we can still debate, and maybe one of you will tell me immediately that there is a particular dual tower of states. I do not know it for this case, but as long as I do not know the dual tower, I take the bound on D strict. And as I have told you, we would also like to see if there's an absolute bound on the number of dimensions. So this is now a little bit vague now. What I take now, I can imagine that R equal to 1 is the smallest possible radius. So I want to see whether the LDC applies for all possible ADS times S compactification with all possible radii. And the one which gives me the strongest bound certainly is R is of order 1. And now, as you can see here, coming back to Miguel's question, if I take proper powers of pi, of Euler number, and so I get something like this. Maybe it's still not, I mean, very illuminating, I would say, not very clear how this could be related to the critical dimension of string theory, but at least it's something of order 10 or something. So it's not completely off scale what we know to have also in critical string theory. Okay.
Can I ask a couple of things here? So where is
yes,
E
sure.
exactly? What was E? Sorry.
E is Euler number 2.7.
Okay. And
comes from the taking log of certain numbers.
Right. And what about bosonic string theory, right? Like that's, so what is your take on bosonic string theory? Like it has a tachyon, that is true, but
yes.
it also has a perturbative limit, and in this limit, the lifetime of the vacuum in Planck units is as large as you want.
Yes, yeah, it's a good comment. I mean, maybe I should have said also before, when I consider now these ADS D times SD prime backgrounds for D bigger than 5, we know, I mean, if we enter the regime of supercritical strings, there is no space-time supersymmetry anymore. So all these backgrounds, all these ADS backgrounds, which I considered arbitrary number of dimensions, must be non-supersymmetric unless there's something which we do not know, but normally they should be non-supersymmetric. For example, for D equal 26, yes, we can have ADS times S in 26 dimensions, but indeed, I believe it would be unstable. But I think it really doesn't really affect my argument so much. And as I told you at the beginning, my approach is not so much to use what we know from critical strings, but to be in a way general open and just look at things from a higher dimensional D perspective.
Thank you.
Okay, maybe there's one thing more which I should mention, and this in a way also limits a little bit the discussion in a particular way. We have basically so far neglected higher curvature effects in our effective action. And they can be also taken into account. So we could, for example, compute various curvature square quantities like these, like the curvature square, the Ricci tensor square, or the scalar curvature square. And they also scale in a particular way with a number of dimensions. And this is a little bit, in a way, unpleasant, because if you compare this with the bound I have shown you before, the bound already is in the regime where curvature corrections become strong. So you may say this is not very good for my bound. So if I'm really strict, I would say I have now 3 regimes, namely the regime when D is smaller than R, and this is coming from the curvature corrections. Then we have small curvature and a good notion of space-time. Then we have the region in between, where D is between R and R square. Here already the curvature becomes large, but still, according to the LDC, we have a good notion of space-time. And finally, when D becomes bigger than R square, curvature is large in any case, but also the notion of space-time breaks down. And here this is where the LDC is started to be violated. Okay, so now, yeah, I'm basically finished. You can also look at the different circumstances and to see whether one can also get bound from different scenarios. One thing, what we did clearly is we obtained the bound, the LDC bound on the number of space-time dimensions as a function of the size of compact spaces. We also looked into black hole physics, and therefore we also obtained a similar bound that D must be smaller than the radius of a typical black hole square, which has to do with the entropy of a black hole, that we do not want the entropy or the number of states to be smaller than 1. So this is another way to get a similar bound. So what I like and what we like to do in the future is, for example, the following. I mentioned you before that it would be nice to get a more general notion of geometric or geodesic distance between geometries of different dimensions. There's still also this issue of back reaction of fluxes at large D, which I think is also not yet fully settled. One could also try to apply the LDC to other backgrounds like tori or orbifolds of large dimensions, and it's also what we are looking at. And I think there are also some nice formulas, some nice equations are popping up. But what I would also find to be interesting is the question, and let me come back to this, is the question of a dual tower. And indeed now, so far I took the point of view that there is no dual tower, but can it be that, that there is indeed a dual tower of states at large dimensions D? If so, according to the philosophy of distance conjectures and duality, there should be a duality symmetry of this type, or of variance of it, where there's a certain coupling which scales like, say, square root of D over R, which is dual to R over square root of D, so to its inverse, basically. And in this way, one could get some kind of interesting dualities, which also include also the number of dimensions. And indeed, if you look closely, and this brings me also back, I think, to Kumon's previous question, if you really look closely, this is also what is, for example, happening in M theory and say 2A or 2B duality, or perhaps even in F theory, if you take F theory as a 12-dimensional theory. And here, indeed, some dual tower of branes indeed can become light in some would-be large D limit. So I think this is also some interesting possibility for ADSD times SD. I think it will not happen, but maybe it could happen in different circumstances. So finally, before I close, I just like to pose again the question how the ADC could be related to the critical dimension in string theory in a more in a more precise way, I would say, for example, to the unitarity of scattering amplitudes in gravity or in quantum gravity. One should also maybe look if there's a non-trivial d-dependence there, and if one can get bounds or constraints from looking at the problem from this side. But I think this is for the future, and with that, I'd like to thank you for your kind attention.
Okay, thanks a lot, Dieter, for the nice talk.